Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you about an extremely important tool in algebraic topology. It's called the fundamental group, and more generally, I want to talk to you about higher homotopy groups. To think about this concept, perhaps one way to understand it is to think about trying to understand topological spaces by probing them with spheres. So why probing them with spheres, you might ask? Well, the point is that the spheres have a special property which allows you to get groups out of this procedure. And once you have groups, you can use all the technology of group theory to try to study topological spaces. Okay, so let's start with our definitions here. So the definition of these higher homotopy groups is quite simple. They're defined most simply for a pointed topological space. So we have the topological space X and a distinguished point X0 here. And what we'll do is we'll consider this as an object in the homotopy category of topological spaces, point topological spaces. So we'll look inside here. So we can also consider a sphere for pi n x0. So n here is going to be some positive integer. Okay, you can look at the n-dimensional sphere Sn, and it's a symmetric object, so you can pick any point on there to get a pointed topological space. And you look at just the morphisms in this category of homotopy category of pointed topological spaces. So in other words, you're just looking at homotopy equivalence classes of continuous maps from this pointed space to this pointed space. The case n equals 1 is going to be called the fundamental group, and that's particularly important. Okay, so let's just think about how we picture elements inside here. Okay, so suppose we have a topological space like this one here. We see there the torus, and we have some distinguished point. I'll pick this x0 here. This is fairly symmetric, so that's not such an unusual choice at all. Okay, and here we have, we're looking at pi 1. So here we have S1, and we've picked a point on there. And I guess what we have here is we have a homotopy equivalence class of continuous maps. So let's just pick one map from here to here. Okay, and maybe the image lies something like this. So P will have to go to X0, and its image might go like this. Okay, and of course you can deform this, so you can sort of slide this around a little bit. Okay, and it'll be the same element. Okay, so that's how we picture one element. Sometimes though, the better way to think about this is to say, well, what determines a continuous map from here to here? Well, firstly, you have a continuous map from the unit interval. That's 0, 1. You can map this down to there like that. Okay, so there's the unit interval from 0 to 1. You can map the 0 and the 1, both get mapped to P. Okay, and then the rest gets wrapped around like that. And you can compose, and basically the continuous maps from here to here, essentially the continuous maps from here to here, which you can think of as paths, such that both the 0 and the 1 get mapped to x0. And if you think of it in this way, okay, and you think of the elements here as being a time parameter, you can think of this as tracing out a path in here. So another way to think of elements of this fundamental group is it's a loop or a path here that begins and ends at x0. Okay, so you trace out the path, and there's a certain direction in which you trace out the path. Now, of course, remember this is only up to deformations. You're looking at homotopy equivalence classes of these maps. So one of the ways that you can deform this map is you can change the speed at which you travel around it. You can, instead of going around in uniform speed, you can go around faster and then a bit slower, because the total time taken should be 1. Okay, and so it's good to think of this as the image of this loop. Okay, so that's why you can really think of it, picture this element as the image of this up to sliding this around. Of course, do be a little bit careful. Going around this way is not necessarily homotopic to going around the other way. So you need to put a direction at which you trace it. But the speed at which you trace it, okay, you can make continuous changes. You can perform a homeomorphism of 0, 1 onto 0, 1. That's orientation preserving, and it won't change that class. Okay, so so we can think of these elements of this fundamental group as loops which begin and end at this x0. Okay, so what's interesting is in the case of this pi n, and in particular for pi 1, you can actually put a multiplicative structure on this, so you can multiply elements. So suppose we have two elements f and g inside here. Okay, so what I want to do is I want to show you a way of combining both of these to get you a new element of this. Okay, so what's that going to be? Okay, so what I need to do is I need to give you, given this f and g, a new map from this circle into x0. Okay, so I'll do it by picture. Okay, because that's the easiest way to really see what's going on. And the key point is the following. It's this first map here. So what you can do is that this map S1, what we're going to do is we're going to map it to something called the wedge of S1 with S1. Okay, so these are, I haven't put the distinguished point in here, but let's suppose there's the distinguished point. We can look at the union, disjoint union, and glue them along the distinguished point. Okay, so here's a purple version and here's the blue version. And what there is there's a continuous map from here to here, which maps the bottom half, this purple bit, into this first S1 down here, and the top half maps into this top bit. So in other words, if you think of this map from here to here as being a path, this is a path, or the loop that goes around like this and then like that. Okay, it's a double loop. Okay, and then what happens? So now you have two circles, and to each of these, and you've also got two maps from circles, okay, to x, and they actually take the distinguished point both to this x0 here. Okay, so what you can do is to this purple circle, you can apply f, and to the blue circle, you can apply g. And this map here, the composite map here, will be called, so this map here is called f wedge g. Okay, that's the composite map. So maybe, I guess more commonly this is called the f wedge g. Okay, and let's give this map a name. Let's call it iota. And so this f composed with g is you first do this iota, and this f wedge g. So just to think about it, what does it mean? Okay, so suppose you have f is given by this loop here, and g is given by this blue loop here. Then this product of these two is given by the loop where you go around this, and then you follow it by this. You concatenate those two loops, and that's what it is. Okay. So I guess one of the things that you do have to do is you have to check that this is well defined. If you replace f with something that's homotopic to it, it doesn't change this, and similarly for g. But I hope you can kind of see, if you just sort of like deform this purple loop or this blue loop, okay, the total loop gets deformed as well. Okay, so that's not a big deal. So I've done this for S1, but there's a similar definition for pi n. Okay, so if you have a sphere, let's imagine a two-dimensional sphere. Of course, what you can do here, what we did was we looked at this opposite point to the distinguished point, and we collapsed it. What you can do is you can look at the equator that sort of contains that distinguished point, and you can collapse it to a point. Okay, and then you'll get two copies of that sphere wedged together at that distinguished point. Okay, so you get the wedge of those two spheres, and then you can apply the same definition to get you a multiplication in that case. That multiplication is rather interesting for higher n because it's actually commutative. Okay, but that's a story I don't want to get into at the moment. Okay, so that's the basic definition of what we have here. We have this set, and we have a multiplication defined on it. And this proposition really tells us why this is a wonderful tool. Okay, so the first thing is this pi n x0 is actually a group. Okay, so we can apply the technology of group theory to it. Okay, the second thing is, okay, so that's a group. So it takes these objects which are essentially in the homotopy category of pointed spaces. Okay, this point homotopy, and it gives you a group. And in fact, this is functorial. So that also means that if you're given a continuous map of pointed topological spaces, or even a homotopy equivalence class of them, okay, you'll get a corresponding map on the homotopy groups. Okay. Functoriality also means what? Okay, so if you aren't so familiar with your category theory, the most important thing is it takes identities, so that's identities in the land of topological spaces, to identities in terms of the group, and also composites, so composites of continuous maps or equivalence classes of them, to composites of group homomorphisms. Okay. So in particular, what you'll get here, because of functoriality, is that if x and x0, y and y0, these two pointed topological spaces are isomorphic in this category, okay, so they're homotopy equivalent in other words, then the gadget that it spits out here, these high homotopy groups, pi n's, are isomorphic as groups. So this is a very, very important property that's going to get used. So essentially it's saying that if you have two pointed topological spaces and you want to say, for example, you want to check are they homeomorphic or not, or even just homotopy equivalent, okay? Okay, so one way that you can do that, and a very, very important way, is to just look at invariants such as the higher homotopy groups. They're just groups, and it's easy to tell whether groups are isomorphic or non-isomorphic usually, and so that gives you a way to check whether the things are not homeomorphic. Okay, this is one of the fundamental reasons for studying invariants such as algebraic invariants such as the fundamental group and the higher homotopy groups. The last thing is that ideally, actually what you want is some sort of algebraic invariant associated to topological spaces, okay? And so it's a little bit subtle the way the theory works in this case, but the key point is the following. Suppose that you have two different points, x0 and x1, and you want to look at these two different pointed topological spaces, x0 and x1. Now, if there's a path connecting x0 and x1, then it turns out that these two higher homotopy groups are actually isomorphic. And in this case, it's a little bit dangerous to do that, so you have to be careful. But commonly, we just define this to be the entire homotopy group of X, okay, with the proviso that, yeah, you have to sort of like be clear that this is only an isomorphism, so it's not defined canonically. Okay, so let's just see basically why it's true. And this is actually just a geometric sort of thing, so I don't want to write down the proof in gory detail. It's more important that you see pictorially why it is true. Okay, so the first thing is that I want to show you why it's a group, and this is very, very interesting in fact, okay? So if it's a group, firstly we have to check the identity, associativity, and inverses, okay? So let's check the identity. So what is the identity here? So what is the identity in this higher homotopy group, okay? So what's the map that you always have? The map that you always have is you can send all of the sphere, the whole sphere, Sn to x0. That's the constant map to x0, okay? So let's see how that works. So why is it an identity? Okay, so we'll do it in the case of pi 1. Okay, so suppose you have a loop like this, right? So remember what you do. So if you want to compose this with this constant map, this identity, why is it an identity? So firstly, what you do, you have this loop which goes around like that, and then you stay there for the constant map. So it's this one composed with staying there. And so, of course, if you just remember, the key thing is basically the image of this path and deformations of it, right? So you can change the rate at which you traverse around this to see that these two are the same. So this path here, this loop here, is the same as if you go around here like this and then stay there for a short while, okay? So that's why that's identity. Okay, what about associativity? Suppose you want to compose this loop beforehand with a loop like this, and a loop like this. Okay. So if you multiply these two first, you go around here, then here, and then this loop here you compose with this one, so you can concatenate with the third one. And of course, that just means that you go around all three loops in that order, in those directions. And of course, you can change the speed at which you traverse them how you like. So that will be the same as if you multiply these two loops first and then that one beforehand. Okay. So that gives you associativity. Okay, so that's pretty nice. The most intriguing and magical part of this, and by the way, yeah, so I guess we've already used the fact that we have to look at homotopy equivalence classes of these two, because it depends on how you trace these around. Okay. The most interesting thing is the existence of inverses. Okay, so suppose you have a loop like this here, and you want to say what's its inverse. Okay, so we want to naturally associate to this an inverse loop, and the loop is going to be basically it's going to be given by the image of this, but you traverse it in the opposite order. Okay, so one way to describe it explicitly is if you have a map from here to here, which represents an element of this fundamental group, what you can do is you can basically do a reflection which swaps 0 and 1, and then do that map, and that will be the inverse. Okay, so why is it that the inverse? Okay, so that's a good question. So firstly, to be the inverse, I guess means when you compose it with the original, you get the identity, and the identity is the constant map here, right? The constant map here. So what is composition? That's the loop, which means that you go here and then you come back. So I need to show that these two are homotopy equivalent, these two loops. Okay, so why is that the case? So basically, what I'm going to do is I'm going to slowly deform the constant loop here to the loop which goes out and back like that. So how do I do that? So firstly, what I'll do is I'll slowly grow this constant loop to this loop here. How do you grow that? So firstly, you start by going slowly out along this path and then coming back. And then you go further out and come back. And then as you go further and further out and come back, you'll eventually get this composite. And this is the composite in both orders. You can do it both ways. And you'll see that in that way, the composite of these two is indeed homotopy equivalent to the constant map, which is the identity. And that proves that this is a group. Okay, so that's wonderful. Okay, so we now have a group. Okay, it's quite easy to show that actually this is functorial, and that's because you're looking at just homomorphisms in this category from here to here. Okay, I won't go through that, but that's standard categorical sort of a thing. Okay, the only thing that needs to be checked is that you do actually land in this category of groups, in the sense that if you have a continuous map from x0 to some other point in space, okay, that will indeed induce a group homomorphism. Okay, but you can kind of see this if you look at images. So if you map these loops over to something else, okay, then the concatenation of loops gets sent to concatenation of loops down there. Okay, so I'll let you check that for yourself, but it's not difficult. Okay, C is also standard category theory. Okay, and in fact, algebraic topology really is something that spurred the development of category theory. Okay, so if you haven't seen this sort of argument, I guess, so why is it true? So if, for example, phi and psi are inverse isomorphisms in this homotopy category, okay, then pi and phi and pi and psi are inverse isomorphisms in the category groups because of this result here. Okay, if you compose them, what you get is pi n of, well, these are inverse isomorphisms, so that's the identity. So pi n of the identity is identity. So the composite of these, it doesn't matter which order you put them in, will be the identity. Okay, so that's rather nice. And so the last thing I want to touch on is why is it that if you change the distinguished point, you get an isomorphic fundamental group or higher homotopic group. And I'll just do it in this simple case of pi 1. Okay, so suppose x0 is path connected to x1. Okay, so here's a path like this. So I want to show an isomorphism between these two groups, and all I want to do is basically tell you how it works, and it takes a little bit of working out to fully establish the proof, but I hope you can see once I tell you what the map is between these two that it ought to be a isomorphism of groups. Okay, so firstly, suppose I want to go from here to here. Okay, so I pick an element inside the left-hand side, which is some homotopy equivalence class of loops like this one here, and I need to get a loop that goes from here. So what's that loop? So remember, these are path connected, so I'm going to pick one path. So unfortunately, there's a choice of path here. I pick a path from here to here, and then I follow it on with this f, and then I do the reverse of that path. So it'll be this one here. And this way, every loop at x0 gets mapped to a loop at x1. And of course, if you slowly deform this loop, blue loop here, that will deform the loop from x1. Okay, and that gets you the isomorphism that you need. Okay, from here to here. Okay, so clearly it's reversible. You can also do the inverse thing. Okay, so the roles of x0 and x1 are symmetric, so you can use this path also to go from loops at x1 can map to loops at x0. And what happens if you want to show that this is indeed the identity? So for example, one of the things that you might want to do is to show that when you go from here to here, okay, here to here and back, you get the same thing. Okay, so for example, to go from here to here, you'll have this loop, and then you get a loop from here which goes around like this. And to come back here means that you have to start from here, and you do the this construction, but swapping x0 and x1. So you go out to here, and then you go around like this, and out to here and back. And that's, since you're adding basically just going here to here and back, okay, that you can homotop back down. Okay, so I'll let you think through that, okay, but that's roughly the reason why that's true, okay, why this gives you an isomorphism. Okay, so this proposition really captures the most important facts about these homotopy groups, okay, the fact that they're groups, okay, and the fact that you have this functor, okay, so it's a functoriality that really does all this hard work for you. And as I said, the most important use for this is to show that things are not homotopy equivalent, and if they're not homotopy equivalent, they can't be homeomorphic. Okay, so let me give you an example of this. So this involves the sphere, okay, and I'll write the sphere as just the unit ball, okay, the exterior of the unit ball inside n+1 dimensional space. And related to that is what's called the real projective space, RPN. And one way to define it, and this is a natural topological way to do this, is to take a quotient of this Sn by the relation which identifies opposite points. So here you have a sphere, you can identify opposite points. So in other words, the equivalence relation is any x is equivalent to minus x, and that's the only equivalence that you have. So they're the only equivalence classes are pairs of antipodal points. Okay, and the wonderful proposition that we have here is that for n greater than 1, Sn and Rpn are not homeomorphic. In fact, they're not even homotopy equivalent, okay? So what's interesting here is, of course, that when n equals 1, so you have a circle, right? And if you identify opposite points on the circle, okay, then, of course, you can sort of like map it back onto, so the two halves back onto itself to get you a circle, and that tells you that Rp1 is, in fact, a homeomorphic to a circle. So for n equals 1, they are isomorphic, but as soon as n is greater than 1, then are isomorphic. And we'll use this fundamental group to show that this is indeed the case. Okay, so let me just show you roughly why it's true. Okay, so here's Sn. Okay, here's a picture. I've drawn the case n equals 2. And what I claim is, or what I want to work out is what is pi1 of Sn. So what are the elements in there? So you have to look at loops inside here, based at, say, x0. Okay, so we just pick a loop like this. Okay, so there's a typical element, and I claim that pi1 Sn is actually just equal to 1. So that means that you can contract this down to the constant loop here. So why is that true? Okay, so let's look at this particular example, okay, and well, we're going to just pick a point which this loop doesn't pass through, this x here. Okay, so it doesn't pass through this point x here. So this is also a loop in Sn minus x. And if you look at the Sn minus a single point, this is homeomorphic to Rn, or perhaps it's easier for you to see that it's homeomorphic to the unit open ball inside Rn. And that we know that's contractible. And so since it's contractible, okay, it's homotopic equivalent to a point, and so its pi1 is just going to be 1. So since you have a loop inside here, any loop inside here that's contractible, you can contract that down to a point. Okay, And so that shows you that this is true for this particular, or at least it shows you that this loop here, you can contract to a point. And I mean, most of the loops that you imagine are going to miss at least some point on the sphere. So you can use this argument. If you have a space covering 1, then you have to modify this argument a little bit, but you can still do it, okay? So the key point is that here, the algebraic invariant you get out is very boring, okay? Pi 1 of Sn is equal to 1, okay? So this is also where we need n is greater than 1, okay? This is no longer true. Okay, this statement here is no longer true when n equals 1, and that's something interesting I want to talk about in a later video. Okay, so let's look at Rpn. To show that it's not homeomorphic to Sn, I just have to find some non-trivial element of pi 1 Rpn. And what's that going to be? So unfortunately, I can't show you precisely why it's non-trivial. You'll have to wait till a later video to see that, but I can tell you what that non-trivial element is, okay? So the non-trivial element is as follows. Okay, so here's maybe your distinguished point. Okay, and what you can do is you can go around, say for example, around the equator to the other side. So here's x0 maybe. And remember, so I guess firstly I should stop here. How do I want to draw this Rpn? I want to draw this Rpn as basically Sn, but you want to think of identifying opposite points. So I've drawn Sn here, okay? I've drawn Sn here, but you have to remember that I want to identify opposite points. And if you identify opposite or antipodal points, that means that this point here is the same as this point here. So this actually becomes a loop. So there's x0 equals minus x0. So here's my loop f. Okay, that's my loop f like that. Okay. So it turns out, and you can kind of think, well, you know, let's just try to move it around a little bit, okay? If we try to move it around a bit, okay, remember the x0 has to be fixed. If you try to move it around a bit, there's no way you can collapse it onto the identity if you just imagine it like that, okay? Unfortunately, that's not a proof, but hopefully I can convince you that, yeah, it looks like it's pretty hard for this to be the trivial element, in other words, for this loop to contract to the constant loop. Now, I want to tell you a little bit more about some interesting things that happen with this group structure. So what I'm going to do is I'm going to square this now, but I want to look at the square. I'm going to basically concatenate this with itself. But remember, one way to concatenate this with itself is I can look at this path, but this is the same as its negative. So we can look at, if we negate this path, okay, we start, instead of here, we look at its negative, and then as you traverse along here, you'll traverse along the back side of the equator like that. So this is also f. So f squared is you go around like this. Okay? And when you go around like this, of course, this is now something you have an actual loop inside the S n, and you can deform that, homotop that down to the constant. So it turns out that in this case here, this f, when you square it inside this fundamental group, you get the identity. Okay, so this is rather interesting. And in fact, what happens in this case is that the fundamental group here, okay, in this example, is actually generated by this element here. Okay, so that's a generator for it. And since we know that its square is equal to 1, this fundamental group is actually isomorphic to Z mod 2Z. So this is a very interesting fact, okay? So this Rpn, it has fundamental group Z mod 2Z, okay, for n greater than 1. And that's why, since this is not isomorphic to the fundamental group here, these are not homeomorphic or even homotopy equivalent. And furthermore, if you can calculate any other topological space and its fundamental group, if it's not Z mod 2Z, then it's not homeomorphic to this Rpn. And that's a very typical usage for the fundamental group. I hope you enjoyed this adventure in pure mathematics.